Today we're going to review some math that's relevant to the study of optimization algorithms. Specifically, we'll review convexity of sets and functions, local and global minima, the Hessian matrix, positive definite matrices, and quadratic functions written using the language of matrices and vectors. First, let's review convex sets. Suppose we have some subset D of a vector space. We say that D is a convex set if for all pairs of vectors x and y within D, and for all real numbers a between 0 and 1, the vector ax plus 1 minus ay is also inside D. The expression ax plus 1 minus ay is an important one to remember and make sense of. First, note that if you plug in 0 for a, you get the vector y, and if you plug in 1 for a, you get the vector x. The set we get by considering all values of a from 0 to 1 is nothing more than the line that connects vector x to vector y. Visually, if D is a convex set and a subset of R, the set of real numbers, then the convex sets are just intervals. A union of intervals is already not necessarily a convex set, as you can see here, because we can pick one point in one of the intervals and another point in the other interval, and there will be some value of a that we can choose, say a equal to 1/2 for this example, such that a times x plus 1 minus a times y is not in our set. If D is a convex set and a subset of R2, it will be a shape such that the line connecting any 2 points in the shape lies entirely within the shape. If you have a shape like this, it's not a convex set because we can pick 2 points in the shape such that the line connecting them is not entirely contained within the shape, such as points x and y in this example. We can use the same intuition for convex sets in higher dimensions. They are shapes such that the line connecting any 2 points in the shape lies entirely within the shape. Next, let's discuss convexity for functions. Suppose we have some function f of vector-valued input x, where x comes from some vector space D. For example, x could be a vector from R2, or it could just be a vector from R1, which is just a real number. We say f is convex if the following property holds. What's this property really saying? If x and y are 2 points in the set, then the set of all points ax plus 1 minus ay, where a is between 0 and 1, is, as we previously discussed, the set of all points on a line segment connecting x to y. So we're saying that the function value at any point along the line segment connecting two input points, x and y, is less than or equal to the corresponding point along the line segment connecting the output points, f of x and f of y. Corresponding point here means the a values are the same. That is, we've scaled the same amount away from the left endpoint of the line connecting the input points as we've scaled away from the left endpoint of the line connecting the output points, also known as the secant line. On the screen is shown an example when our function's input is just a real number. The function shown is x squared over 16, which is convex because for any 2 points we choose, the function value is always under the secant line. That's what it means to be a convex function. For real valued functions of 2 variable input, a quadratic function would again be an example where the graph of the function lies below the secant line between any 2 points on the graph. Let's move on to minima of functions. The point x star is called a global minimum of a function f if the function's value at x star is less than or equal to the function's value anywhere else in the domain. The point x star is called a local minimum if the function's value at x star is less than or equal to the function's value anywhere else in a small enough neighborhood around x star. This means if you zoom in enough, the lowest value that f appears to reach will occur at an input of x star. A global minimum is said to be strict if the value is strictly less than the value anywhere else in the domain. And likewise, a local minimum is said to be strict if the value is strictly less than the value anywhere in a small enough neighborhood around x star. Note that all global minima are local minima, but not all local minima are global minima. We can also clarify a minimum to be isolated or not isolated. If it is isolated, there's some small enough neighborhood where it's the only local minimum. It might be hard to visualize a minimum that's not isolated at first, but the scenario that comes up most often is that of a function that fully flattens out somewhere, so that there are instead infinitely many minima that are all equal to each other in function value. As you might remember from Calc 3, a local minimum requires that the gradient of your function be 0 if the gradient is defined. This is known as a necessary condition for local minima. But one thing that's usually not covered in Calc 3 is that at a local minimum, it must be that the Hessian matrix is positive semi-definite. If you remember what this means, you can skip the following explanation. First, let's discuss what the Hessian matrix is. It helps to think of the Hessian matrix as the second derivative of a function that has vector-valued input. Let's get our symbol straight first. Let's say our function f takes a vector x as input, where x is itself a vector with entries x1, x2, and so on up to xn. The Hessian matrix is found by differentiating the gradient of the function, which we consider to be a column vector here and for the rest of the video, where by differentiating, we mean building a matrix whose kth column is the element-wise derivative of the gradient of f with respect to the kth input variable. In other words, the entry ij in this matrix is the derivative with respect to xi and then with respect to xj. As an additional fact about the Hessian matrix, if you have a little vector delta x and left multiply it by the Hessian matrix, what you get is approximately the vector change in the gradient vector of the function by taking that little step delta x. This approximation becomes better and better as we make delta x a vector of smaller and smaller magnitude. The Hessian is the Jacobian matrix of the vector-valued function defined by the gradient of our scalar function f. Once again, the Hessian is a matrix-valued function of vector-valued input. Now that we know what the Hessian matrix is, let's cover a little more terminology. A matrix A is said to be positive definite if for all vectors x that are non-zero, x transpose times A times x is greater than 0. Here times means matrix multiplication. This is nothing more than the dot product of x and ax being greater than 0. You can think of this as saying that multiplying the vector x by the matrix A does not produce a vector that's too different in direction from x. If ax was orthogonal to x, x transpose ax would be 0. And if the direction were too far away, the dot product of x and ax would be negative. It turns out that there is an equivalent definition of positive definiteness that ends up being more useful to us. A matrix A is positive definite if there's some value c greater than 0, such that x transpose ax is greater than c times the squared magnitude of x. Essentially, x transpose ax is bounded below relative to the squared magnitude of x. This is the definition we'll actually be making use of in future videos. We can understand this better if we go to the basic case where A is simply a real number, that is a 1-by-1 matrix, and x is just a real number, that is a vector of length 1. In this case, x transpose is just x, and the vector and matrix multiplications are just regular multiplication of real numbers. So what we get is a quadratic monomial with coefficient a. Any choice of c less than a will satisfy the statement in our new definition for positive definiteness. Finally, as you might imagine, a positive semi-definite matrix is one where x transpose ax is greater than or equal to 0, meaning we've relaxed the greater than to a greater than or equal to. For the last topic in this video, we're going to make clear why we care so much about these different matrix definitions. Let's look at how we can write a multivariable quadratic polynomial in matrix and vector language. What do we mean by a multivariable quadratic polynomial? We mean a function of the form seen here, where every term is either a variable squared times some constant, a product of exactly two variables times some constant, the product of exactly one variable and a constant, or a constant. For now, never mind that we have a factor of 1/2 next to the constant coefficient on the squared terms. Note that if we consider the n inputs as a vector of length n, and the n coefficients on the degree 1 terms as a vector of length n, and consider the coefficients on the product and squared terms as the following symmetric matrix, then we can write this polynomial as follows. 1/2 x transpose ax plus b transpose x plus c. Note that the b transpose x is a dot product of vectors. It's straightforward to see where the b transpose x and plus c terms come from in our polynomial. But what about the first term? Let's multiply it out from right to left to check. First, ax is the following. Next, x transpose times that result, meaning we take the dot product of vector x with the vector ax, gives us the following. And recall that aij equals aji. So when we multiply the whole thing by the coefficient of 1/2, we get exactly what we had above in our polynomial, which I encourage you to verify for yourself. What's nice about this is that we can express quadratic polynomials using the language of matrices and vectors. To finish the video, let's look at differentiation using the matrix vector form of polynomials. Suppose we have a function f as follows. Remember that differentiation in this context means to take the gradient, which will end up being a vector. To find the gradient, we need to differentiate with respect to each variable. Starting with variable x1, let's expand the form of this function. That is, let's actually write out all the multiplications. You can do this again for yourself for practice, but I'll just paste what we had earlier. After differentiating with respect to x1, we get the following. Next, differentiating with respect to x2, we get this. Continuing in this way, we get the following for the gradient, which can be simplified to the nice expression ax plus b, which may be very familiar to you from linear algebra. Let's summarize what we've discussed in this video. First, we discussed convexity for sets, which just means you can draw a line between any 2 points in the set without leaving the set. Then we discussed convexity for functions, which means the secant line always lies above the graph of the function in some sense. Next, we discussed minima, where the global minimum is a point where the function value is lowest compared to all other points in the domain, and local minima are points where the function value appears lowest compared to all other points within view, if you zoom in close enough. The Hessian matrix is an important matrix that's comprised of second derivatives of a scalar function of vector-valued input. It's the Jacobian of the gradient. Matrices A are said to be positive definite if the dot product of x with ax is always positive for all non-zero vectors x. Finally, we can express a quadratic polynomial in multiple variables using the following matrix vector expression, and the derivative is just ax plus b. That's all for this video. Thanks for watching.